Hey there, awesome physics students. Let's talk about energy, one of the most useful and powerful ideas in all of science, including physics, chemistry, biology, and beyond. The reason energy is such a useful and powerful idea is because it has its own conservation law. That is, under certain circumstances, the amount of energy in a system will be constant. It may transform from one form into another, but you cannot create it or destroy it. It will always go somewhere from one place to another place, and all of it will be accounted for. One of the advantages of energy is that it is a scalar, which means it's just a number, has no direction information. In contrast, momentum, that also has its own conservation law, is a vector. So you have to think about direction when you're thinking about momentum conservation. We want to talk about energy conversions and in different forms, in different scenarios. And to do that, we want to come up with some categories here for different forms of energy. So let's talk about these briefly. There's kinetic energy, which is energy of motion. That's energy because a thing has a velocity. Elastic potential energy, that's the energy stored in springs. So if you stretch or compress a spring, you're storing elastic potential energy in the spring. But other things, remember, can act like springs. So any material that can bend or twist or stretch or compress, and it wants to go back to its equilibrium position, which pretty much includes all materials, will have elastic potential energy. Gravitational potential energy is energy that's shared between us and the Earth because if we increase our distance away from the Earth. And we can get this out. So imagine if you carry something up and you drop it. Because you've increased the distance, you can extract that gravitational potential energy back out and convert it into kinetic energy, for example, if you drop something. Sound energy is pretty self-explanatory. Those are energy that's stored in pressure waves. But remember, sound can travel through air and liquids and solids as well. Mostly we'll experience it in air. Light is also pretty self-explanatory, although again we're going to include other forms of electromagnetic radiation on the electromagnetic spectrum. So that includes infrared, including visible light, but infrared, X-ray, gamma ray, radio waves, those are all forms of light, even though we can't all see those and we don't usually call them light. Thermal energy is a really interesting category. A lot of energy can hide in this category. This is just heat energy. At the microscopic level, it's because objects are atoms, and those atoms have, even in a solid, they will be in their equilibrium position, near their equilibrium positions, but they'll actually be bouncing around. So they'll have some kinetic energy, and they behave like springs with their neighbors. So they'll have some elastic potential energy. The energy at the microscopic level of these two categories, we experience that as heat or thermal energy. And we say things have a temperature, and the temperature increases as that energy category increases. Okay? Chemical energy is one that we see a lot. Batteries have chemical energy. They convert chemical energy through a chemical reaction into electric energy, which is down here. But one that you've participated in, probably even today, is when you eat food, the chemical energy that's stored in the bonds of the chemical bonds of the food, we can store in our bodies in ATP, ADP, and then we can use it to do different things like throw a ball and give it kinetic energy or something like that. So this is a big one with animals. Here is chemical energy. Finally, we have electromagnetic energy, which is anything that we're going to throw into that category of like electricity. For example, if you plug in a space heater, you're converting electric energy, that would fall in here, into thermal energy, which would be here. The unit for energy that we're going to use is the joule, and a joule is just 1 Newton times a meter, so it can be broken down into other units. A more common unit that you've probably seen before is the capital C calorie, the food calorie. And that one converts into 1,000 of the lowercase calories that you've probably seen in chemistry. This is the energy needed to heat up 1 gram of water 1 degree Celsius. We see often food has the calories listed in, the amount of energy in that food listed in calories, but you could list it in joules just as well. And some countries do this. The conversion between these is 4184 joules is 1,000 lowercase calories, or this is often called a kilocalorie because 1,000 is a kilo. Let me just, before I finish here, let's just talk about a couple of different examples of a conversion process that we might think of. If you have a calculator, you have light energy in the space in the room that's landing on the solar cell that is converting. That solar cell then converts that light into electric energy in the calculator. There's a small amount of waste heat that occurs in that process. And then we can do calculations with it. And again, while we're doing that, a small amount of waste heat will be produced. Too small for us to notice with our hands, but if you imagine like a computer that's basically a super powerful calculator, you can really notice that waste heat. Another common one that you've participated in is if you run up the stairs. When you're running up the stairs, you're converting chemical energy that's stored in your body from the food that you eat, and you're converting that into kinetic energy and gravitational potential energy because you're increasing your distance from the center of the Earth. And so that energy goes into the Earth-U system, and you get that kinetic energy that's associated with your velocity as well. But of course, some of that energy, not all of the chemical energy goes into those two categories. A lot of that energy actually goes into thermal energy, heat energy. So that process of converting that is not completely, utterly efficient, and so there's some waste heat. We call it waste heat because it's not what we ultimately desire. But from an energy standpoint, it's all fine. And all of that energy will be accounted for. So this is the idea of energy, and we're going to use this a lot. It's a really powerful and useful idea.